Car direction of movement with the imagination of left or right hand via EEG signals. Let's have a little preview of what we are going to see in this presentation. I have divided most of the presentation into three parts, actually three steps. I will explain method we used and the corresponding result in each step. And the steps are data acquisition, signal processing, and avatar control. After that, we will have a conclusion and future work. The first step is data acquisition. Uh, we have recorded our signals via a system with the following properties. An EEG headset channel at a frequency of 250 Hz, a 32-inch LED monitor to visualize instructions and a Unity environment for the user, a head holder to avoid EMG noises and neck tiring of the subject, as you can see on the right of the screen, and that one is me. And moreover, we used a Faraday cage to block electromagnetic fields and reduce noise. We collected the data from 5 subjects, all male in the range of 20 to 40 years. We provided an introductory session for each subject if it was necessary. 500 trials were recorded from each subject in 5 sessions, 100 trials per session. Each trial consisted of a 2-class motor imagery task that the subject should imagine right or left hand movement. Each trial started with a 1-second display of the fixation point on the center of the screen. The subjects were instructed to imagine right or left hand movement for 1 second, and then the subject could rest for 2 seconds. After recording the raw signals, we go to the next step, signal processing to interpret the command signals. We can break down the signal processing procedure into 4 steps. The input is the raw signal we collected in the last part. EEG signal is very susceptible to noise. We implemented a head holder and a Faraday cage to avoid some of them happening. However, many noise sources still affect the signal and reduce the signal to noise ratio. So we should first make the signal as clean as possible in pre-processing step. Then we should extract some features from the signal in order to have something to classify. After that, we must select preferred features to feed the classifier. Finally, we classify the selected features with appropriate classifiers and translate the raw signal into command signals. Now let's discuss each step individually. Pre-processing step. First, we have cleaned the line frequency with a 50 Hz notch filter. Then a bandpass filter was applied between 0.1 and 45 Hz. If you remember from the data acquisition part, each trial was 5 seconds last, but the first 1 second and last 2 seconds were not a motor imagery task. We removed them here. Excuse me. Then we draw the signals and check that there are no errors during the sessions for channels like disconnection. If a channel had unrealistic data, we remove it. Then, if we have removed any channel in the last step, we generate the signal by interpolation and put it in the place of the removed channel. After that, we re-reference each channel by subtracting the average of the signal from each channel. Finally, we extract epochs from each trial and remove the baseline. We have selected 5 features to extract from each trial: variance, skewness, kurtosis, band power, and log power. We extracted each feature in 2 domains, time and frequency. After we extracted our features, we applied common spatial pattern to make our classes more distinct by these features. After we extracted our features, we should select some of them to classify. A preferred feature is a feature that makes our classes as distinct as possible. To sort our features in distinctibility order, we used false discovery rate, which allocates a number to each feature with this formula. When a feature gets a high rate, as we can see here, the denominator should be high. So mean of classes is far from each other, and the denominator is low. So classes are more concentrated. Therefore, a high rate means that the feature distinct to classes well. With this selection method, we selected the first 10 features to classify. Now that we have our preferred features, we classify them using five classic classifiers. Linear discriminant analysis, support vector machine with linear kernel, k nearest neighbor with k equal to 10, Gaussian naive Bayes, and decision tree. We used k-fold cross-validation with k equals to 10 for reporting the results, and the results are, as we can see, the best validation accuracy we got is 88.9% with LDA. After generating the control command signal, now we can control an avatar in Unity. For syncing MATLAB and Unity, we use the serial method. We have three text files in this method, two of them specifying the turn, one for each program, and one of them to share common information. Assume that the MATLAB turn is true and the Unity turn is false. And we know that both cannot be true nor false. Uh, so MATLAB turn tells the MATLAB that it's your turn. MATLAB interacts with the shared information file, reads the data, and applies the changes if necessary. Then makes the MATLAB turn false and Unity turn true. Again, now that Unity turn is true, MATLAB turn is false. Unity turn tells the Unity that it's your turn. Unity interacts with the shared information file. Then it makes the Unity turn false and MATLAB turn true. Uh, we have translated the right command to 1 and the left command to -1 in our case, and fed it into a simple car control Unity game. The car moves forward by default, and we just change the direction. As we can see in the video, uh, it's it's worked without the lag. We conclude that it is possible to classify motor imagery EG signals with classical classifiers in acceptable accuracies. We saw that LDA had 88.9% accuracy, and we saw that we can sync MATLAB and Unity with serial method for normal NOR gaming without lag problems. The refresh rate was about 0.1 seconds for this research. And future works are we are going to real-time neurogaming that we're working on it now, and implementing eye tracker to omit eye related artifacts, that is my thesis commitment, and testing neural classifiers to increase accuracy and decrease time cost. Thank you for your attention. If there are any questions, please feel free to ask.
Thank you for your sleek talk. Anyone has any questions, please raise your hand. Dr. Pachanari, please.
Thank you for your presentation. I have a question about data acquisition. You said that you um, gather information in three parts, and in data processing, you told that you omit the first part and last part. I just wanted to know why you gather this information and then you omit this information.
Uh, it's because we when we tell the person to concentrate and imagine left and right hand movement. The first second that the fixation point appears that we can see in the middle of here, this helps. This is supposed to help the subject to concentrate, and that 2 seconds after the motor imagery task is for rest. That the subject cannot uh, continuously do the motor imagery task. It's so tiring, and that is why we did this. Uh, I don't know.
Okay, thank you.
Oh,
Thank you.
you're welcome.